Hello, this is Christoph Mussenbrock of Etherisc. I am very grateful to be part of EDCON 2020. We founded Etherisc in 2016, and in the past 4 years we spent a lot of time to explore the regulatory frameworks for blockchain-based insurance. And it was very hard, and many times we thought it's impossible to fulfill the regulatory requirements. But today I want to show you a new promising legal model for blockchain-based insurance. It's a genuine new approach and it works only with blockchain. So we think this is a very natural and typical application of blockchain technology to the financial industry. But let me tell you the whole story from the beginning. 2 years ago, we called the German financial authority BaFin. Hello, this is Etherisc. We want to build an insurance business. They told us, okay, the only thing you need is 5 million euros. We said, we don't have that much money. Aren't there any exceptions? But they simply said, no, no exceptions. This year, we called again, and let me explain what happened in between. Insurance is highly regulated in most countries. Usually, insurance is a legal promise to pay a compensation in case of a loss. Luckily, Germany has a formal definition for this, but it is very similar in other countries as well, for example in the US. The legal promise to pay in case of a loss is the root cause for a pile of regulations and the reason for high minimal capital requirements, and these are usually in the millions, creating a high entrance barrier for new market participants and disruptive products like ours. But why do we need all of this? Regulations have been created for good reasons. Regulations have 3 main objectives: to avoid monopolies, to avoid negative externalities, so negative effects on third parties, and to avoid information asymmetries. These objectives shall mitigate unfair and unethical behavior of market participants, and they shall stabilize the market. Consumers need to be protected. If someone promises you something, you should get what you expect. And consumers need legal guarantees so they can sue the company. And the same applies for investors. And you need legal enforcement, because regulators need effective measures. All of this shall create trust between market participants, be it consumers, investors, or producers. But in many cases, trust by regulation can be very expensive, and people can build trust by other means. Especially for retail products, legal enforcement is pointless due to time and cost of enforcement. For many retail products, we don't need and want legal enforcement. Instead, simple market mechanisms provide much better consumer protection. Think of a vending machine. If the machine doesn't work, you won't sue the owner. It is in his own interest that the machine is working properly, and otherwise he'll lose his customers. But how can customers trust an insurance product without legal enforcement? The answer is smart contracts. Smart contracts provide the means to ensure proper and transparent execution. Gives the consumer a bulletproof insurance product based on smart contracts, and she won't need a legal guarantee. Replace legal guarantees by technical guarantees everybody can check. and let's see how this could work in practice. Maybe you remember, this is our flight delay insurance. Select a flight and then pay the premium, and finally you are informed that you don't get a legal guarantee for your payout. That's it. Your policy is processed by a smart contract, and you can check the proper processing directly by examining the code and the transaction. If the code is correct, your policy will be processed correctly, and the provider won't be able to mess with it. What's the consequence? We explicitly exclude any legal guarantees for a payout in case of a loss. And therefore, one crucial element of an insurance contract is missing. And therefore, this is not an insurance contract, according to German law. And if it's not an insurance contract, then there is no regulation. If there is no regulation, then you don't have regulatory costs, and you don't have 5 million euros minimum capital. Of course, consumers need to be well informed that they don't get a legal guarantee. So, this year we called the German regulator BaFin again. We explained our concept and asked, hey, if we exclude a legal guarantee, will it still be an insurance contract? And BaFin said, no, it won't be an insurance contract. And we asked, if we offer such a product, then we are not subject to the whole pile of regulations? And the answer was, yes, indeed. No regulation, no minimum capital requirements, no 5 million euros needed anymore. We can start our business with much lower capital. And so currently we are working on an implementation of this model. And we also think that this could be the blueprint of a whole class of innovative insurance products. But beware, there is no insurance contract, and therefore we may not call it insurance, because this would be misleading. Instead, we use the term protection. And you don't pay a premium, but instead a service fee. Because what we actually do, we offer only the service to run a set of smart contracts. So stay tuned. Thank you for watching, and goodbye.
Well, this is going to be fun, I must admit. This is my first pandemic conference. I'm so glad I have a standing desk here so I can be walking and hand gesturing. Sorry if it bothers you too much in a remote setup. This is how I roll when I'm presenting to people. Anyway, hi again. I'm Kuba Kucharski. I'm Chief Product Officer at Golem, and I'll be talking today about where Golem is and where we're going with this thing. And probably the best way would be to start with showing you this slide about our history. Um, so, two things that are important here. First, we are old crypto-wise. We started early. We are pre-Ethereum. So we had a lot of iterations already, a lot of lessons learned. And our last release is Clay Golem. And we actually helped developing a use case recently called Chem at Golem, and it performs simulations of chemical reactions that are forming a network. And this later is being used in a health industry to develop new medicines. And we're very excited about this because this brings us closer to one of our goals to being a platform, like a public good platform. And we will be porting this use case to new Golem, but for now this is on legacy. And this kind of gets us to the token migration thing. You might be aware or not, our token GNT is not ERC20 compatible. This is because we are an old project again, and the ERC20 token was still being discussed at the time. It was like not obvious to use it when the contract was being created. And this is something we definitely want to change. So the token migration is coming, and you will be able to migrate your tokens to new token. And there are multiple reasons we're doing this, but probably the most important ones are feature reasons. So we need things like gasless transactions, layer 2 scaling solutions, support for smart contract wallets. These are all the things that comes with ERC20, and this is why we're migrating. And so what Golem is? Golem is this completely new set of protocols, and they all come together to create this platform for resource sharing. And this means like discovery, matching, selling, buying. I mean, all possible types of computing resources. You can think CPU, GPU, storage, network, but also think about things like unique hardware. So let's say you have a telescope and you want to monetize your telescope by sharing it with other people. You could be doing this with Golem. This is how extendable the protocol is. And of course, because this is new architecture, it is also a completely new code base, and the new code base that is written in Rust. I wanted to show you a slide about architecture, just one slide with the architecture of new Golem. And I want you to remember two things from this slide. First, there are two types of nodes in Golem network: requesters and providers. And the second thing is all the boxes that you see on this slide are interchangeable. This is how modular and open the system is. And this is not just a theory, this is something that we're doing right now. For some time, we had like a centralized implementation of our marketplace, and now we have a decentralized implementation, and we're plugging this into new Golem, and this is just a feature flag. This is how easy it is. So how are we building this? Of course, we Golem, we are defining these protocols. We are writing our own implementation of these protocols. However, we're working like very closely with developer community every step of the way, getting feedback, doing surveys, demos, private feedback sessions, and we will continue to do so. And we actually call new Golem like a developer-oriented Golem, because this focus on developer experience is something of a great importance for us. And we're constantly thinking, what is missing? What are the obstacles from the point of view of the developer? What can we remove? What kind of design patterns are there that we should deliver? What kind of usage patterns we should deliver? What is the lightest possible development environment that will allow you to start tinkering with Golem? How to make the learning curve as shallow as possible? Actually, let me share a slide with you. This is Python code using new Golem platform and using our experimental high-level API for new Golem. And this is that simple. You just define what your worker should be doing, in this case, rendering one frame in Blender, and then in the other section, you're defining how to split your task in general, like in this case, into sending multiple frames to multiple providers. And that's it. There is one more thing that is actually very interesting here. On top of this slide, you will see like image hash. This is actually linking to the image. This image has been converted just by using our command line tool from like a plain Docker Hub image. So you just need to make sure that the image is the image allows to run your code, and that's it. The definition of the memory and storage here is actually optional, but you can define it here too. If you're a developer and this is still rocket science to you, that I don't know what to say to you. No, actually, scratch that. We will make it even simpler. We'll be working on making this even simpler. I think we're kind of in a good place already, but for some use cases, for some usage patterns, we can make it even simpler, right? Imagine like just using a Python decorator to tag the functions that you want to execute on Golem. Now, the second thing that I wanted to talk to you is payments, because payments often introduce a lot of friction, and probably previous speakers at the conference already mentioned a lot transaction costs, so I don't need to dive into this. Golem has never required you, and new Golem will never require you to execute costly smart contract interactions just to perform things like discovery, matching, and agreements. This is all happening in our marketplace, so all you have to do is just pay for the work, and these are just like simple ERC20 transfers, and we know this is much cheaper than smart contract operations. But on top of that, like our priority is to deliver like a layer 2 driver for payment module. And yeah, so like it will be no crazy overhead on performing operations on Golem. It will be a non-issue general. Okay, so sometime in April, Vitalik tweeted something like this. And he tweeted about mechanism design punk, and then someone replied with the name system punk. And I actually read it one day later, and for me this was like 420, so my mind exploded. How magnificent this system punk name is. I love it. And yeah, but jokes aside, I actually think that this is what we're building here. This sturdy, safe building material that you need to build system punk applications. So I'm not saying, don't build legacy thing, don't build things that will allow scientists or enterprises to scale their computations. Please do build them. This is a valid use case for Golem. But think, what kind of applications would really benefit from values like censorship resistance, distributed trust, permissionlessness? Here are some things that you could be building with Golem. And imagine that you have a plugin in your browser that automatically detects deepfake videos, but under the hood just sends the links of the videos to Golem network that analyzes them, and this is how you know. Or imagine like a Moloch DAO version where members are not afraid to vote publicly on something because their vote stays anonymously. Like imagine the app analyzing satellite maps for illegal tree cutting or illegal buildings that would be like founded and supported by the community. These kinds of apps are very exciting to us because they benefit from our unique value proposition. Okay, so where we are with that. The best thing is new Golem works. And it works since April. And as I mentioned before, like we're replugging some things like the market implementation to have a decentralized implementation. We're still working on a lot of things around the SDK and testing. We're building these high-level APIs. We're working on layer 2 payment drivers. So there is still much to be done before MVP, but we're not going to wait for MVP to show you all of this. Actually, we're planning like an alpha release, like a developer preview really soon. So you will be able to run it for yourself. You'll be able to just go and write your simple requester code and run it in Golem. You might be asking, so what MVP is? For me, MVP is when the network and the protocols and the implementation is ready to host application that has productional users. And this is what we're aiming for MVP. And yeah, of course, there will be like 2 execution environments, WASM and VM execution environment, layer 2, payment driver, 2 high-level APIs, but also we will be preparing inspirational packages for developers. And I mean, not just ideas, but, pieces of product research and tech research and maybe some pieces of code and pair it with like a bounty program. So developers can just take it and start writing and deploying these apps as soon as possible. So yes, we will not be writing use cases ourselves, but we will be the stewards of the community and we'll make sure that these applications will be created. Yeah, so I think that's it. If you feel that this is something that is interesting for you, that you would like to write an application on top of New Golem, please do contact us. And also check out the release that is coming soon. There will also be like a reason to talk to us and give us feedback. We welcome this every freaking time. Thank you so much for having me and listening, tuning in to this presentation. I hope you have a great rest of the conference. Talk to you soon.
Hello everyone, my name is Jae-Yun Kim, Ph.D. candidate studying blockchain at Virtual Machine and Optimization Lab at Seoul National University in Korea. In this session, I will talk about our research paper named Ethanos, optimizing synchronization for lightweight client on account-based blockchain. As Ethereum becomes popular, the storage size of Ethereum continues to increase. Therefore, the size of archive node is more than 4.8 terabytes as of August 2020, which takes several weeks to bootstrap as a full node. FastSync significantly reduces the storage size, but still, it takes more than 445 gigabytes as of August 2020, which takes several days to bootstrap. The bootstrapping process is to synchronize to the current state in the latest block to execute or validate new transactions. Archive sync downloads all the transactions and replaces them from the genesis block to the latest block, so it is very slow but completely secure. On the other hand, FastSync downloads all the transactions but replaces only the recent ones, which occurred after the pivot block, that is 64 blocks behind the latest block. Since FastSync forgoes generating the histories of the intermediate state trie, it significantly reduces the download data and bootstrapping time. However, it is still slow and burdensome. Why is the FastSync still burdensome? It is because state trie synchronization requires numerous disk IOs. State trie is a data structure to store accounts with their histories, and the number of accounts exceeds 108 billion as of August 2020. It was efficiently designed, but as the number of users and accounts increases, the tree becomes very large, and it causes the storage and bootstrapping problems. This is due to the way state trie updates accounts. When an account is updated, Ethereum creates and inserts new trie nodes as many as the height of the trie. Therefore, the larger the size of the trie, the greater the trie grows. For example, Figure 1, the left shows that block state sigma I of the block I consists of 5 accounts whose addresses are 0xA7D391, which is A1, and 0xA7D397, which is A2, and so on. We represent an address with 6 characters for simplicity and assume that all accounts are EOA. If the block I plus 1 contains one transaction, that transfers 5 Ethereum from the account A2 to the account A4 with a fee 0.01 Ethereum. As a result, the balance of A2 decreases from 45.01 to 40 Ethereum, and the nonce increases by 1. Also, the balance of A4 increases from 0.12 to 5.12 Ethereum with no change of its nodes. A5 is the miner of the I plus 1th round, so the balance of A5 is incremented by 2.01 Ethereum, where 0.01 Ethereum is the transaction fee and 2 Ethereum is the block reward. This constitutes I plus 1 as depicted in the middle of the figure. As you can see, there is only one transaction, but 12 trie nodes are newly created and inserted to the database, as you can see below the figure. A block of Ethereum contains about 200 transactions on average, so 1,000 of trie nodes are created and inserted in each block. And the increasing quantity continues to increase as the trie grows. However, with careful inspection of Ethereum, we discover that almost all accounts are dormant. For example, only 5% are active in 1 month, and only 3% are active in 1 week. Also, we observe that many accounts are likely to be updated soon after they are updated. For each account, we measure the average time distance between two consecutive updates and classify the accounts by the average time distance. We can roughly interpret that an account is updated in a week with a probability of 76% and in a month with a probability of 90%. So we propose an idea named Ethanos to sweep dormant accounts periodically to reduce the state try overhead, just like Thanos, who wiped out a half of all life in Avengers. To achieve the goal, Ethanos defines an epoch, epsilon, the number of blocks after which Ethanos sweeps the dormant accounts periodically. We call the last block of an epoch a checkpoint. Since it is extremely expensive to traverse a state try to find and remove dormant accounts, Ethanos simply creates a new empty try every time a new epoch starts, and fill it with the active accounts used by the transactions in the new epoch. Consequently, a miner or a verifier will execute a transaction as usual, using the new try to find and update the accounts involved with the transaction. Since the try is initially empty, however, no account is available, so Ethanos caches the state try of the previous checkpoint and use it for finding an account state as well. That is, if an account used by a transaction is not available in the new try, we search for it from the cached try, and if it is there, copy it to the new try, and then update it as a result of the transaction. If the account is available in neither of the tries, when the account is a sender of a transaction, a restore transaction will be used, as will be explained later. At the end of the current epoch, Ethanos caches the current state try, discarding the old cached try, and then starts a new epoch, and the same process repeats. The primary reason that Ethanos caches and uses only the state try of the previous checkpoint is that this will allow a full node to bootstrap only with a single try, thus reducing the drown node size. Also, it will make every full node behave the same, instead of using multiple cached tries by some nodes while using one cached try by others, following the redundancy spirit of the blockchain. Finally, the state tries of consecutive checkpoints will include many redundant active accounts, so it is more efficient to use only one. Since Ethanos efficiently reduces the state try size, the increase of state try slows down. As you can see in this figure, the number of accounts is decreased from 5 to 3 at the next epoch, and also the newly inserted try nodes, which are decreased about 3 at the first and second blocks. The effect will be bigger if there are more accounts. These days, Ethereum has more than 100 million accounts. If a transaction uses a dormant account in the current epoch, Ethanos first reactivates the account by creating it in the current state try. There are two cases. If the account is a sender of a transaction, it should first transmit a restore transaction, which will create the account in its last account state. If the account is a receiver of a transaction, there are two possibilities. One is that the account is a dormant account, and the other is that the account is a new account, since in Ethereum, when someone sends some value to an arbitrary address that does not exist in the current state, a new account for that address is created in the state with a non-stop 0, regardless of the existence of the owner, as A6 in figure 4. In Ethanos, we simply create a new account even for the former case. which can reduce the frequency of the restore transactions. We call this crumb state of the dormant account. If such a dormant but newly created account becomes a sender later, yet without enough balance, it will restore itself by merging its account state with the original state. A restore transaction is initiated by the owner of a dormant account, but the transaction itself is created and transmitted by an archive node on behalf of the owner. Then, miners and verifiers will run the transaction as other regular transactions. So, there are three rules involved. The owner should first determine if its account is dormant by checking if 2 epoch periods have passed since the last occurrence of this transaction, or by inquiring if its account is accessible in the current epoch. If the account is used once in a while, the owner may use a running smart contract to request a restore transaction regularly. An archive node who gets a request from the owner will create a restore transaction by accessing the state tries of relevant checkpoints and collecting the essential data, which include a marker proof of the account at the last active checkpoint and void proofs of the account at each checkpoint from the last active checkpoint of the latest checkpoint -1. That is, a restore transaction should have a proof that the account was active at the last active checkpoint and was inactive thereafter as depicted in Figure 5. However, a void proof for the last active checkpoint is not necessary, as it can be checked through a cached state try. The miners or the verifiers will execute the restore transaction when it is transmitted in the transaction pool. They will verify if the marker proof and the void proofs are correct using only the state root in the checkpoint block headers, and create the account in the current block state try. We reduce the void proofs by using Bloom filters as depicted in Figure 5b, and design the merging process for crumb states as depicted in Figure 6a. Also, we prevent already restored state to be restored again as depicted in Figure 6b. We implemented Ethanos based on GES version 1.9 and compared it with the original GES client. The evaluation was conducted on a machine depicted here. And there are several constraints to experiment Ethanos and original GES with the real Ethereum data from 7 million to 7.3 million blocks. For archive node, Ethanos reduces the storage size about 10%. For fast sync, at the 7th checkpoint, Ethanos slightly reduces the storage size. However, for compact sync, which is proposed sync mode that does not download the transactions before the pivot block, Ethanos significantly reduces the storage size about 62%. And this figure shows that the storage size of GES fast, Ethanos fast, GES compact, and Ethanos compact sync. Ethanos fast is almost same as the GES fast because of the overhead of the additional restore transactions. However, the gap between Ethanos compact and GES compact is continuously increasing. The slight increase of Ethanos compact is caused by the block headers. Finally, we measured the synchronization time for the 4 cases. As you can see, both Ethanos fast and compact syncs are faster than GES fast and compact syncs. And the bootstrapping time of GES fast and compact are almost same, although the storage size of GES fast sync is about 60 times of that of GES compact sync. This means that the state try is the real bottleneck of the bootstrapping process. That's all, and if you have any questions, feel free to mail me.